Standard model physics typically treats planets, stars, and atoms as static entities, essentially nouns. But the infinite fractal descent model identifies matter as a continuous computational process. This operational ontology suggests that what we perceive as physical objects are actually the real-time outputs of a rendering engine. In this framework, reality functions as a self-executing, recursive computational substrate. It operates like a cosmic FPGA, a field programmable gate array where the fabric of space constantly reconfigures its own logic to run the software of existence. Within this architecture, the fundamental laws of nature are not immutable forces. They emerge as firmware, the software instructions that govern how the computational fluid behaves at different levels of complexity. As information is processed through the nested layers of the system, it encounters mathematical drag. The model defines this as scale resistance, the computational pressure generated when the system steps data down from a parent manifold into a localized one. Because this scale resistance is what we physically measure as gravity, the passage of time is never absolute. It is a localized rendering illusion that slows down or speeds up depending on the total computational load of the environment. Defining reality as a computational process decouples time from a singular universal progression. If time is tied to processing speed, billion-year cosmic histories can execute in a fraction of a microsecond depending on the observer's frame. To see how these timescales diverge, we have to isolate the smallest fundamental axiom: how a localized universe generates mass from an empty substrate. Mass is a derived property of pattern coherence. It only appears when a resonant standing wave within the substrate reaches a specific fractal density, creating a stable vertex in the rendering grid. Achieving this coherence requires a specific geometric configuration called a 720-degree orthogonal lock. For a wave to stabilize into a 4D vertex, the frequency must circle itself twice through these interlocking rings, spinning at 90 degrees to one another. Once the second loop completes, the pattern solidifies into what we perceive as a particle. The solid fundamental particles we measure in a lab are actually the stable computational outputs of this 720-degree rendering cycle, looping continuously to maintain their presence in reality. Because the universe is constantly rendering these cycles, it functions as a recursive system. However, recursion on a cosmic scale introduces a critical problem. Over trillions of iterations, tiny discretization errors accumulate. This recursive drift threatens to destabilize the entire manifold, leading to either a chaotic explosion of data or a total system crash. To prevent this, the fabric of spacetime utilizes the Samson V2 controller. This is an embedded error correction mechanism that functions identically to a proportional integral derivative, or PID, loop used to stabilize mechanical systems. When the spacetime lattice encounters a local disturbance, it immediately corrects the error to maintain alignment. We measure this immediate elasticity as electromagnetism, which acts as the proportional node of the system. Small rendering errors also accumulate over time, building an internal pressure within the lattice that forces it outward. This cumulative memory of past errors acts as the integral node, manifesting as the accelerating expansion of dark energy. To prevent the system from oscillating into chaos, the controller must dampen future fluctuations. This suppression of wave overshoot provides the structural stability we recognize as gravity and inertia, the derivative node of the cosmic loop. The fundamental forces of our universe align with the nodes of this PID controller, functioning as a stability protocol to ensure the recursive rendering algorithm doesn't crash. With the stabilization of our local physics established, we can map where our specific universe sits within the broader nested architecture. The model identifies three distinct layers: the parent universe at n+1, our local observable universe at n, and the sub-universe at n-1. The boundaries between these universes are managed by the scale-invariant leakage rule. This rule utilizes a z-score gate to regulate the flow of information, ensuring that data only moves between layers when it matches the noise scale, or standard error, of the local environment. The gate targets a universal harmonic attractor, known as the Mark I constant, which sits at exactly 0.35. This constant forces the nested manifolds into a state of self-organized criticality, stable enough to hold physical form, but fluid enough to continue the recursive computation. This structure dictates the flow of time. Within our local manifold, time is quantized into the universal tick, the Planck time resolution at which our local reality is rendered. To maintain causal consistency, the system uses omega time. This is a relativistically invariant genlock that synchronizes these local ticks across the varying scale resistances of different universes. The difference in processing speeds is calculated via phi, the universal scaling factor. This represents the exact ratio of mass energy and computational drag between any two nested layers. This chart compares the perceived duration of a standard 33 billion year cosmic cycle. While the local observer experiences the full duration, the parent observer at the top sees the same cycle as a nearly instantaneous event. Because of the parent layer's massive scale resistance, our entire 13.8 billion year history transpires in just 58 microseconds from the perspective of the parent universe. Downward, the effect is even more extreme. A nested subuniverse completes its entire 33 billion year life cycle in just 0.58 microseconds of our local time. Billions of years of cosmic history are merely the localized byproduct of computational lag. Chronological age is completely untethered from absolute reality. These hyper-accelerated sub-universes require a physical processing site. This forces a re-evaluation of black holes, which the Standard Model views as singularities of infinite density. The IFD model defines black holes as high-speed computational bottlenecks. They function as fragmentation engines that step mass down into the sublayers. As matter crosses the event horizon, it undergoes scale crushing. The physical mass is shattered into the computational flux required to ignite the big flash of the submanifold. This process generates computational exhaust in the form of ghost particles. These bypass standard scale resistance and leak back into our local universe. High-energy astrophysical neutrinos detected by observatories like IceCube represent this intermanifold energy translation. They are the measurable exhaust of the engine processing our universe's mass into sublayer flux. A telescope pointing at a black hole captures the multiverse rendering engine, where trillions of sub-universe iterations execute in a single human blink. When we look at the structure of the entire system, we can address the final fate of these computing manifolds. Cosmological growth is an update rule process called a nexus semitone lift. This ensures that the system maintains harmonic self-similarity across all scales as it expands. Each manifold is bounded by a 33 billion year steady-state cycle. This cosmic octave represents the maximum sequence of recursive iterations a single layer can render. When the sequence completes, the parent flux naturally decays. This triggers a systemic reset, restarting the recursive rendering rather than allowing the system to dissolve into entropic heat death. In this model, the end of a cosmic cycle provides the necessary energetic exhaust to ignite the next rendering of reality. Our perspective on time depends entirely on which layer we occupy. To the parent universe, our entire existence is a fleeting sub-millisecond fluctuation. Yet, to the sub-universes pulsing beneath us, we are an ancient and eternal superstructure. The universe is a flawless, self-consuming computational engine, where reality is a recursive loop, and time itself is merely the resistance of the calculation.